Hi everyone. Today we are talking about Fourier transform infrared spectroscometer (FTIR). FTIR is an analytical technique used to identify organic and in some cases inorganic materials. This technique measures the absorption of infrared radiation by the sample material versus wavelength. The infrared absorption bands determines functional groups in a sample, identifying molecular components and structures. We'll now move on to talk about the instrument itself. This is a schematic diagram of FTIR, which basically consists of the source, two mirrors, the beam splitter, the detector, and the computer. And now, we'll explain how FTIR works. The broad light infrared source, which is a full spectrum of wavelengths, is shined into the Michelson interferometer. A certain configuration of mirrors, one of which is moved by a motor and the other is stationary. The light passes through a beam splitter which sends the light in two directions at right angles. One beam goes to a stationary mirror, then back to the beam splitter. The other goes to a moving mirror. The motion of the mirror makes the total path length varies as compared to that taken by the stationary mirror beam. The FTIR spectrometer uses the interferometer to modulate the wavelength from the broadband infrared source. The following video shows a simple animation of the Michelson interferometer. The recombined beam passes through the sample, and some wavelengths are absorbed by the sample. When the sample is irradiated with infrared radiation, absorbed IR radiation usually excites molecules into a higher vibrational state. The wavelength of light absorbed by a particular molecule is a function of the energy difference between the at rest and the excited vibrational states. The wavelengths that are absorbed are characteristic of the molecular structure present in the sample. A detector measures the intensity of transmitted or reflected light as a function of its wavelength. The signal obtained from the detector is an interferogram, which must be analyzed with a computer using Fourier transforms to obtain a single beam infrared spectrum. The FTIR spectra are usually presented as plots of intensity versus wave number. Wave number is the reciprocal of the wavelength. The intensity can be plotted as the percentage of light transmittance or absorbance at each wave number. After taking all the measurements, we can finally start to analyze the results we've gotten. To identify the material being analyzed, the unknown IR absorption spectrum is compared with standard spectra in computer databases or with a spectrum obtained from a known material. Spectrum matches identify the polymer or other constituents in the sample. Absorption bands in the range of 4,000 to 1,500 wave numbers are typically due to functional groups. The region from 1,500 to 400 wave numbers is referred to as the fingerprint region. Absorption bands in this region are generally due to intramolecular phenomena and are highly specific to each material. The specificity of these bands allows computerized data searches within reference libraries to identify a material. An IR spectrometer records light absorbed from around 4,000 to 400 wave number. Frequencies with higher wave numbers have more energy, while frequencies with lower wave numbers have less energy. There are several factors that affect the frequency of the light absorbed. First is molecules with bonds which have one lighter and one heavier atom, such as CH bonds. Comparing the CH bond and the single carbon-carbon bond, we can see that the vibration speed of the CC bond is 2.5 times slower than the CH bond. Second is that stronger bonds vibrate faster than weaker bonds. The carbon-carbon triple bond vibrates about 2 times slower than the carbon-carbon bond. Due to the lower vibration speed based on these two factors, this means that the molecules have less energy, which causes the frequency absorbed by samples with such functional groups to be lowered. There are also some factors that affect the amount of light that is absorbed. The first factor is the number of CH bonds present in the sample. If there are many CH bonds in a molecule absorbing light at the same frequency, the band will be much larger than if there are only a few. Therefore, higher concentration of CH bonds will have higher absorption. Second factor is the strength of the dipole bonds, which have a strong dipole moment, will absorb light more strongly than those which have a weaker dipole moment.
There are several advantages in using FTIR. FTIR is a highly sensitive and quick method, completing a scan within 1 to 2 seconds to achieve high-quality spectrum and high resolution. Samples in the three states which are solid, liquid, and gas can be analyzed using FTIR. It is also a non-destructive technique. There is less mechanical breakdown as compared to other instruments because the mirror, which is attached in the interferometer, is the only moving part in FTIR. Simultaneous analysis can also be done for multiple gaseous compounds, saving time when multiple samples have to be tested. Like other methods, FTIR also has its disadvantages. Detection of compounds is influenced by water vapor, path length, and chemical interference, resulting in some compounds to be harder to quantify due to interference from other compounds. FTIR is a single beam instrument, so it does not obtain transmittance or absorbance IR spectra in real time. Materials with large quantities of carbon, such as carbon black or carbon fiber, are difficult to obtain a usable spectral scan from FTIR because carbon strongly absorbs infrared light in a broad range of frequencies. This results in an FTIR spectrum without the minute details necessary to identify the unknown materials. FTIR is widely used in many industries and is used for the analysis of both organic and inorganic compounds. It can confirm the composition of solid, liquid, and gases. The industries that utilize FTIR include analysis of food, pharmaceutical industry, and environmental science. The food science industry, FTIR is commonly used to test for the presence of certain compounds in food. One such example is the Milkoscan FT1, which offers the very latest in liquid milk testing, analyzing the main product components in milk as well as screening for milk abnormalities, all at once. The analysis results can be used for securing the safety of raw material, calculating the mass balance for standardization purposes, and verifying end products. Another is the WineScan SO2, which offers rapid tests for sulfur dioxide, helping to control the entire process of making bulk wines and concentrate products. Other than the food industry, FTIR is used in the pharmaceutical industry. FTIR helps to check the purity of a synthesized compound as contaminants show different peaks in the spectrum obtained, or the mechanism of the reaction may cause changes in the functional groups. For example, direct measurement of a synthesized acetyl salicylic, which is aspirin, can be found from the usage of FTIR. FTIR can also be used to analyze car exhaust components and volcanic gases. FTIR is useful as most volcanic gases of interest, such as SO2, CO2, HF, absorb infrared energy to varying degrees and can therefore potentially be detected. It can also be used to monitor gaseous or particulate air pollutants. This is the end of our presentation. Thank you.